All right, so welcome back. I threatened last time to develop the Hardy-Weinberg Equilibrium, and that's what we're going to do today. The Hardy-Weinberg Equilibrium was developed by two researchers, obviously Hardy and Weinberg. They developed it independent of each other. This was back in the days before communication about research was all that easy. They developed it independently of each other, but because that communication wasn't there, they both published independently of each other, and so we give both of them credit. I find it's easiest to start talking about Hardy-Weinberg equilibrium by talking about something that we're already pretty familiar with, which is some basic genetic approaches. I'm going to switch over to another marker. It's been threatening to go out for a while now. I think it's finally given up the ghost. Let's say I had the following Mendelian cross here, a heterozygote times a heterozygote. And I wanted to predict out what the expected genotypes along with the expected frequency of these genotypes would be in the next generation. And what I could do is recognize that this individual has two alleles, and each of these two alleles are the probability of contributing each of them to the next generation is an equivalent probability that goes back to one of Mendel's laws of independent assortment. And we could say that the probability of contributing a big A allele to the next generation is 1/2, and the probability of contributing a little a allele to the next generation is 1/2. The same probabilities hold for the other parent, so therefore the probability of generating an individual that's homozygous dominant would be the probability of parent 1 contributing a big A multiplied times the probability of parent 2 contributing a big A to the next generation. Okay? So if this probability is 1/2, that's 1/2 times 1/2, or 1/4. So the probability of getting this genotype is 1/4. Because both of these events have to happen together, we use the multiplication symbol. I like to think of this as the terminology and. Parent A has to contribute a dominant allele, and parent 2 has to contribute a dominant allele in order for this to happen. The and language is multiplication and probability. Same probabilities hold true for the homozygous recessive. That's the probability of picking a little a allele from the first parent and picking a little a allele from the second parent, which I hope you see is also 1/4. Now, the probability for the heterozygote is a little bit different. It's either I pick a big A allele from the first parent and a little a allele from the second parent, or I pick a little a allele from the first parent and a big A allele from the second parent. And is multiplication, or is addition. So this would be 1/4 plus 1/4 equals 1/2 probability of the heterozygote. Now, this is the way that Mendel pretty much laid out his probabilities in his 1865 paper on genetics. But it didn't take the biologists long. It took a long time because Mendel's work wasn't actually discovered until the early 1900s by a guy named Hugo de Vries. He was a pea plant researcher and stumbled on Mendel's paper on peas, and then got to reading it, and it was like, oh my God, it was one of those holy grail moments, and boom, genetics started. In any event, once people found Mendel's paper and started getting into it, we're biologists, we don't tend to like all this kind of gobbledygook. So it didn't take long before another biologist came up with a way to approach these probabilities that didn't involve doing the probabilities, and that's our buddy Punnett. Punnett developed this idea of a Punnett Square, and in the Punnett Square, you give the genotype of the parent as the two alleles and the other parent as the two alleles, and then you just kind of match up these genotypes of the offspring. But Punnett was kind of smart because the probabilities are inherent in the Punnett square without us having to do all these complex probability calculations. After all, the big A, the homozygous dominant, is in 1 out of 4 boxes, and therefore there's a 1/4 probability of producing that genotype, 1/4 probability of producing the homozygous recessive, and 2 out of 4 boxes is equal to 1/2 probability of producing the heterozygote. So the Punnett square actually is a way to circumvent these mathematical calculations. It gives us the probabilities already. But going into it, we know that the probability of picking each of these alleles from a parent during meiosis is 50%. Well, we're going to use a technique analogous to this with the population. We have a bucket of alleles here, right? A bunch of big A's, a bunch of little a's in the population. And let's say that we know what the frequencies are of these two alleles. We've counted them in the bucket, we've counted which ones are which, and we know the frequencies. So I'm going to use an analog to this Punnett square where I'm going to put the frequency of the big A and the frequency of the little a in my Punnett square. And I can ask a question, well, what's the probability of reaching into the bucket and pulling out a big A? Well, the probability of doing that is equal to the frequency of that allele. The probability of pulling out a little a is equal to the frequency of pulling out, a frequency of that allele in the population. So the probabilities are equal to the frequencies. So those of you that have had statistics, what I'm going to do is sampling with replacement. Those of you that haven't had statistics, don't worry about it. What really is going on here is I'm not really pulling alleles out of a bucket in so much as an individual is copying his or her allele and sending it to the next generation. So this is a sampling with replacement type mechanism, because if I give a big A allele to my offspring, I'm not really giving them my allele. It's not like I don't have it anymore. I'm just giving a copy of that big A allele. Okay? So what is the probability of reaching into the bucket and pulling out two big A alleles? One big A allele and then another big A allele if I'm sampling with replacement. Now, if we were in class, usually somebody at this point says 25%. And then I go, well, no. Because the difficulty here is transitioning from this Punnett square to this one. In this Punnett square, the frequencies of these two alleles in individuals are 50%. But in the bucket, these frequencies could assume any value, right? The frequency of the big A could be 60%, and the frequency of the little a could be 40%. They don't have to be 50%. In fact, I would argue that they're probably not 50% in a majority of cases, the vast majority of cases. Okay, so let's think about this purely mathematically. The probability of generating an offspring that's homozygous dominant is equal to the frequency of the big A allele times the frequency. So this probability is actually this. And the probability of reaching into the bucket and pulling out two little a's is equal to the probability of pulling out that little a, which is the frequency, times the frequency. If I reach into the bucket and pull out a little a first, that's given by its frequency, followed by a big A, or I could reach in and pull out a big A, followed by a little a. The commutative property of multiplication says A times B is equal to B times A, and therefore these two numbers, whatever they are actually the same. Okay? Now, this mathematical language is not so much fun either, so what we're going to do is clean this up a little bit by just coming up with variables to represent each of these. So I'm going to say P equals the frequency of the big A, and Q equals the frequency of the little a. And that means that my Punnett square now looks like this. And the probability of pulling out two big A's is equal to P squared, P times P. Two little a's is given by Q squared, and then pulling out a little a followed by a big A is QP, and a big A followed by a little a is PQ, but PQ equals QP, so I'm just going to write it as PQ. Now, I've given in this Punnett square all of the possible combinations of alleles that could happen, right? I've done that, and therefore all of these probabilities should sum to 1. P squared plus 2PQ plus Q squared then equals 1. This wonderful thing is the Hardy-Weinberg Equilibrium. And they generated it using this kind of Punnett square thinking that Punnett first proposed for predicting offspring genotypes and frequencies. Okay? All right, now, these values here really represent expected frequencies of genotypes. P squared equals the expected frequency of the homozygous dominant in the next generation. The expected frequency of the heterozygote is equal to 2PQ because there are two ways to get it. Either you draw a big A and then a little a, or a little a followed by a big A. And then finally, the expected frequency of the homozygous recessive would be given by Q squared. Now, Hardy and Weinberg were smart enough to know that there's a lot more that goes on with reproduction and organisms than just dumping alleles into a bucket and pulling them out one at a time, right? Reproduction is far more complicated than reaching in and pulling out an allele, writing it down, and pulling out a second allele and writing it down. So their argument was that these are actually the genotypic frequencies that are expected if we follow certain rules with the alleles in this bucket. Following certain rules with the alleles in this bucket. Because really what Hardy and Weinberg have set up with this Hardy-Weinberg equilibrium is what's called a neutral model. Neutral models are models that predict values if there's no change. Okay? If we do certain things in a certain way with this bucket of alleles, these are what we predict. But in order to predict that, we have to make assumptions of no change. In other words, we can't allow certain things to change within the bucket, because if we allow those things to change, our predictions won't be valid. Okay? So the neutral model predicts what happens if these changes are not allowed. What Hardy and Weinberg then did was come up with a list of things that you had to assume did not occur because they could alter the outcome. Okay? So these are referred to as the assumptions of the Hardy-Weinberg equilibrium. Okay? The assumptions of the Hardy-Weinberg equilibrium. So I've got my bucket of alleles. What things do I have to assume about those alleles in order to keep the frequency of the alleles in the bucket constant? Because if the frequencies stay constant, then my Hardy-Weinberg expected expected genotype frequencies can be predicted from the allele frequencies. In other words, if I know what the allele frequencies are in the bucket, I can predict what the frequencies of these genotypes will be in the next generation, but only if these frequencies stay constant and some other things stay constant. So one of the assumptions that you have to make is that you can't change the alleles into other alleles. So this allele can't get up one morning and spontaneously say, I've had it with being a little a, I want to be a big A. And at that point, I've changed the frequency of the alleles in the bucket. I've reduced the frequency of the little a, and I've increased the frequency of the big A by changing one allele type into another. Well, it is possible biologically to take this DNA molecule and copy it into the next generation and make a mistake, change one allele into another, and that particular process we call mutation. Okay, we're going to call this mutation. So we have to assume in Hardy-Weinberg that mutations can't occur, because if they occur, they mess up our predictive ability. The model doesn't hold true anymore. All right, number 2. There can't be any differences in allele fitnesses. Okay? If there were differences in allele fitnesses, that would mean if I pulled out a big A, this big A could copy itself 3 times, and the big A allele can only copy itself once. There are differences in the ability